What I want to look at here is perpendicular distance, which we talk about with regard to torque and angular momentum. We've done this a couple of times, but I thought a little review would help. I think the first example I gave you was sort of when we were looking from the back of a vehicle going round a corner, and if it's going round a corner to the left, then we're going to need a centripetal force that way. And so we say, where does that come from? Well, the car's trying to push out that way, and we get a friction force that way. And if we wanted to look at this force and ask how much torque is it applying to the vehicle, then what we would need to do, we go with the centre of mass there, and we draw a line down that way, and we say, well, we can't just use the force times that distance, if we call that d, because that force is not perpendicular to that lever arm. We would need to take the component. So to actually work out the torque there, we would have to go torque is equal to force times the distance times the angle between the force and the perpendicular there. So if that was our theta, then it would just be that force times the cos of theta. Depends which angle we use, but you can see that's what we'd have to do. Now, the easy way to do that saves you doing that angular piece, and if we'd used the other angle there, the actual angle between the two vectors, that is this little angle there, then it would have been the sine of the angle, right? Because those both add up to 90 degrees. So what you actually can do is just extend from that center point a line in the direction, or in a direction which is parallel with the force. And instead of using d, use this distance here. Okay, so if we call that x, then the torque is actually equal to the force times x. And we don't have to worry about that cos of theta or sine of theta depending on which angle we use. Now in vector mathematics, then the actual torque is just the force cross product the r, which is a position vector, and that's just equal to the magnitude of the force times the magnitude of the vector times the sine of theta. They use the angle between the two vectors, which is that one and that one, so they use the alpha, so it comes out like that. But that all works, but we don't do that in high school. We could do it about level 2, I think I've told you that before. So we use what I call the perpendicular distance. Okay, so again, I'll try and make it clear because it's not like that. If that was your distance, this was your angle of your force, then you would just extend parallel to that force a line, and when you got at right angles here, then that distance, we'll call it x, times the force would be the torque. So we call this the perpendicular distance. Now we can also do it with angular momentum. If we've got a planet, or it doesn't matter what, just any point, we've got an object with a velocity, the angular momentum about this point, the center of this planet, would normally, this is the angular momentum formula, remember this one where we use mvr. I use that little perpendicular symbol to realize that we do it this way. Normally we would just do vr, r is just the distance, and again the vector mathematics, the cross product, will take care of everything. But since we don't do that, we can just extend back from our velocity vector until we've got right angles, and then our distance becomes this one. Alright, and so the actual distance we use is not r, it's the perpendicular distance, which is x, and that's how we would work it out. Okay, so remember that comes into play in these torque problems and in these angular momentum problems.